Somewhere out there, in the darkness between the stars, there's a place where the laws of physics as we understand them simply stop working. Not slow down, not weaken, stop. A region of space so warped by gravity that light itself, the fastest thing in the universe, can't escape it. We're talking about a black hole. And today, we're not just going to describe one from a safe distance. We're going to fall into one. Step by step, kilometer by kilometer, we'll trace exactly what would happen to your body, to time itself, and to the universe around you, right up to the point where our current understanding of physics runs out of answers. This isn't just a thought experiment for fun. Some of what you're about to hear has actually been observed, measured, and photographed by real scientists. Let's begin the fall. Before we start falling, we need a sense of scale, because black hole is a term that gets thrown around so casually that its true horror often gets lost. A black hole forms when an extremely massive star collapses in on itself at the end of its life, crushing an enormous amount of mass into an impossibly small space. The result is a gravitational field so intense that it creates a boundary in space called the event horizon, the point of no return. Cross it, and no signal, no light, no information of any kind can ever come back out. Some black holes, called stellar mass black holes, contain roughly 5 to 20 times the mass of our Sun, compressed into a region just kilometers wide. But at the centers of most galaxies, including our own Milky Way, there are supermassive black holes, containing millions or even billions of times the mass of the Sun. The one at the center of our galaxy, called Sagittarius A star, is about 4 million times more massive than the Sun. For our journey today, we'll imagine falling toward a supermassive black hole. Not because it's less dangerous, but because, strangely, it's the only kind of black hole a human could survive crossing into, even briefly. We'll explain exactly why very soon. Here's something that makes this entire journey feel less like fiction and more like a preview of something genuinely real. For decades, black holes were purely theoretical, predicted by Einstein's equations but never directly observed, because, by definition, they emit no light of their own. Then, in April 2019, an international collaboration called the Event Horizon Telescope released the first ever direct image of a black hole's shadow, a supermassive black hole at the center of a galaxy called M87, roughly 55 million light-years away. The image showed a glowing ring of superheated gas swirling around a dark central void, the black hole's silhouette, cast against its own accretion disk. It took a network of telescopes spanning the entire planet, working together as one Earth-sized virtual instrument just to capture that single image. It remains one of the most significant confirmations in the history of physics that these objects are exactly as strange and real as Einstein's math predicted over a century earlier. Let's begin our descent. From a great distance, say a few million kilometers out, a black hole's gravity behaves almost exactly like any other massive objects. If our Sun were somehow replaced with a black hole of equal mass, Earth's orbit wouldn't even change. We'd just lose our sunlight. But as we approach, accelerating under the black hole's pull, something starts to feel different. Space itself begins to curve more and more sharply around us. Light from distant stars starts to bend visibly as it passes near the black hole, smearing background starlight into strange arcs and rings, a direct visual signature of spacetime being warped by gravity. At this stage, you'd still be perfectly safe. The real danger doesn't begin until we get much, much closer. As we close in on a stellar mass black hole specifically, we'd encounter something with a genuinely unsettling nickname among astrophysicists: spaghettification. Gravity doesn't pull on every part of your body equally. It pulls harder on whatever is closer to the black hole. For a small, stellar mass black hole, that difference in pull between your head and your feet over the short distance of your own body becomes so extreme that you'd be stretched, violently, irreversibly, into a long, thin strand, like toothpaste squeezed from a tube. This would happen long before you ever reach the event horizon. This is exactly why our journey today focuses on a supermassive black hole instead. Because a supermassive black hole's event horizon is so much farther from its center of mass, the tidal forces at the horizon itself are actually gentler. Strange as that sounds, the bigger black hole is, in this one specific way, less immediately violent to fall into. A human could theoretically cross the event horizon of a large enough supermassive black hole without being torn apart on the spot. Here's where things stop being just about gravity and start becoming about the fabric of reality itself. As you fall closer to the event horizon, Einstein's theory of general relativity predicts something extraordinary. Time, from the perspective of anyone watching you from a safe distance, appears to slow down. To an outside observer, you would appear to move slower and slower as you approach the horizon, your image growing dimmer and more redshifted, seemingly frozen at the boundary forever, never quite crossing it. An optical effect caused by light taking longer and longer to escape the intensifying gravity. But from your own perspective, falling inward, nothing would feel unusual at all. Your personal clock would tick normally. You'd cross the event horizon in what feels like an ordinary moment, completely unaware, at least locally, that you just passed the point of no return. This isn't speculation. This exact form of gravitational time dilation has been measured and confirmed near far less extreme objects, including precise atomic clock experiments here on Earth that detect tiny time differences based on altitude alone. And now, the moment itself. You cross the event horizon. From your perspective, there's no flash, no wall, no dramatic barrier. Space at this boundary isn't physically different in any way you could locally detect. But the moment you cross it, something profound has already happened. Every possible path through spacetime available to you now leads only deeper inward toward the center. Moving away from the black hole is no longer just difficult. It's not a direction that exists for you anymore, in exactly the same way that yesterday isn't a direction you can walk toward. You are now irreversibly cut off from the rest of the universe. Any light, any radio signal, any final message you tried to send back out, none of it will ever reach anyone outside. From this point forward, you exist inside a region of space-time that no observation, no rescue, no physics experiment from the outside universe can ever access again. Before we go deeper, here's a second real scientific milestone worth pausing on. In September 2015, the LIGO Observatory detected something humanity had never directly measured before: gravitational waves, ripples in space-time itself, produced by two black holes, each about 30 times the mass of our sun, spiraling into each other and merging into one over 1 billion years ago. The collision released more energy in a fraction of a second than all the stars in the observable universe combined, radiated out not as light, but as literal ripples in the shape of space and time. By the time those ripples reached Earth, they stretched and squeezed the fabric of space-time by a distance thousands of times smaller than the width of a proton, and LIGO's instruments were precise enough to detect it. It was direct proof that black holes aren't just theoretical shadows in mathematics. They're real, physical objects, massive enough to shake the universe itself when they collide. Once inside the event horizon, our journey continues toward the center, and here's where honesty matters more than spectacle. Nobody actually knows, with certainty, what happens next. General relativity predicts a singularity at the very center, a point of infinite density where the equations themselves break down completely and stop producing meaningful answers. Space and time as concepts essentially lose their ordinary meaning. Some physicists believe quantum effects, not yet fully understood or unified with gravity, would take over well before you actually reach that mathematical singularity, potentially replacing it with something stranger and possibly less infinite. What we can say is this: any structure, any body, any organized matter falling inward would continue to be stretched by increasingly extreme tidal forces, eventually broken down at the level of atoms, then atomic nuclei, then further still, into the most fundamental particles physics currently recognizes. This is the question that captures the public imagination more than almost any other in astrophysics. Could a black hole ever release what it swallows? For decades, the standard answer was simply no. Nothing crosses the event horizon and returns. But in the 1970s, physicist Stephen Hawking proposed something that reshaped the entire conversation. Black holes aren't perfectly black after all. Through a quantum effect now called Hawking radiation, black holes very slowly leak energy back into the universe over unimaginably long timescales, gradually losing mass and, in principle, eventually evaporating entirely. Though for a black hole of stellar or supermassive scale, this process would take vastly longer than the current age of the universe itself. Some theoretical work even suggests that any information about what fell in might, in some scrambled, currently not fully understood form, eventually be encoded in that radiation. It's one of the most actively debated open problems in modern theoretical physics, a genuine unsolved mystery, not a settled fact, and it's part of what makes black holes one of the last true frontiers where fundamental physics is still being written. You will, almost certainly, never come anywhere near a black hole in your lifetime. The nearest known one to Earth is still thousands of light years away. And yet, this journey we just took matters far beyond morbid curiosity. Black holes are, in a very real sense, natural laboratories for testing the absolute limits of physics. Places where gravity, time, and quantum mechanics all collide in ways we can't recreate anywhere else in the universe. Every real observation we make of them, from that first photograph in 2019 to those first gravitational wave detections in 2015, is quietly rewriting our understanding of space and time itself. In other words, the most inescapable, destructive objects in the known universe are also some of our best teachers about what reality is actually made of. If you enjoyed this journey to the edge of physics, subscribe to the channel and let me know in the comments, what should we fall into next?